In this video, we're going to do the pH scale and how it relates to calculating the pH of strong acids and do some calculations on those strong acids. So the pH scale is based on the concentration of hydrogen ions, only on hydrogen ions, nothing else in your course. And it varies approximately between 1 and 1 times 10 to the minus 14 moles per decimeter cubed of those hydrogen ions. And that is approximate. Now, just to remind you, here's the pH scale again. You've got your alkalis up here and you've got your acids down here and then neutral in the centre according to a universal indicator. The range is really large. This is a really large range. So this is a 1-mark question that might get asked. Now, the range is so large and we use a logarithmic scale. Now, this logarithmic scale is the button in your calculator that you just type log, you put minus before it and then put log and then put in the number here and you'll get the pH. And this is a really, really important equation to remember. And most of acids is about remembering about 4 or 5 key equations that you can interchange between each other. So here is your first one. Now, why do we use that logarithmic scale? To make the numbers more manageable. If I can say, write something down here for that 1 mark that you might miss is, why do we use a logarithmic scale? To make the numbers more manageable because there's such a large range. Now, or we can calculate the opposite. We say, let's calculate the H plus using 10 to the minus pH. Now you go onto your calculator and you press Shift Log, and the Shift Log will give you this 10 button here. Then just put minus whatever your pH is, and you can work back to the H plus. And that's going to be a very regular use in this acids part of the course, this having minus log and then turning to 10 to minus. Okay. Now, really, really important is the exam tips. pH values in any of these calculations are written to 2 dP and there's no units. Really, really important. A lot of the time people miss it. They don't do 2 dP. That means if something has a pH of 7, 7 is not the pH. 7 is not the pH. 7, it is 7.00. If you have 11, it will be 11.00. You have to put the 2 dP in all the time. I can't emphasize that more, and no units. The negative sign here means that as your pH increases, the concentration of hydrogen ions decreases. So let's have a look at the pH scale. That means down here, okay, you're getting, this number is going down. As the number goes down, the hydrogen ion concentration goes up, and as the number goes up, the hydrogen ion concentration goes down. We're just using hydrogen ions to calculate our pH. Now, without using a calculator, we can do something quite simple. So here we have the pH scale, and I've highlighted 1, 7, and 14. And we're going to write our H plus concentrations across the top. Now, if you've done this at GCSE, you might already know how to do this, so please go ahead and do it. But how could we calculate the hydrogen ion concentration, but without a calculator? So what we can do is we can look at the number here and say if something is pH 1, this only works with whole numbers, by the way, only works with whole numbers. All we do is raise it to the negative power of the pH number. So that means the hydrogen ion concentration is 1 times 10 to the minus 1. So we then go here, the hydrogen ion concentration will be 7, and then take that, raise it to the negative 1 times 10 to the minus 7 H plus concentration, and then 14, 1 times 10 to the minus 14. You just take this number and raise it to the negative power 1. So that would be 1 times 10 to the minus 1, 1 times 10 to the minus 7, 1 times 10 to the minus 14. And that's a very, very easy way, and they can do this in tests, to do it without a calculator, where you can then take the hydrogen ion concentration and then put it into pH equals minus log of H plus to get your pH back if you want, okay? Or you can use it in another one of our calculators, which is more likely. In another one of our calculations, we'll use H plus from this. So now we're going to do a reminder of strong and weak acids and do some calculations of strong acid pHs. So first of all, we've got 2 examples here. And we've got hydrochloric acid, which I've said is your strong acid, and ethanoic acid, which is an example of a weak one because it's carboxylic acid. Now there is a bit in between both of these where we will talk about later, where you can't really use either of the ways in which we calculate the pH in this course to calculate the pH very accurately, okay, because they're right down the middle. Because strong and weak is not a separating line. They're weak, they're strong. They mix over, okay, because you can't just get something that's fully dissociated versus something that's partially dissociated. You can have some that's 99%, 88%. They're so close to being a strong acid they kind of mix. But again, we'll talk about that later on. But for now, we can show a distinction between just strong and weak. For now, we're just going to say strong and weak. So let's start off with strong acids. Now, strong acids completely dissociate, and these are the ones I expect you to remember. Okay, and they have generally those colours with a universal indicator. Now, the equilibrium goes completely to the right. Okay, so that basically means all acids are in equilibrium. Okay, and you can see they're all reversible arrows. And that also means that 1 mole per decimeter cubed of the monobasic acid will give 1 mole per decimeter cubed of the hydrogen ions. So if we put that in equation form, we're going to say if we have 1 mole of this, it's fully dissociated. So all of this will be completely to the right, and it will fully dissociate to form 1 mole of this and 1 mole of the NO3 minus. Because it's fully, so this 1 mole will turn into 1 mole of this and 1 mole of this. And essentially you'll have nothing left here. Okay, so 1 mole will give 1 mole and 1 mole. Now, if we do that, and we do that with a dibasic acid, we expect 1 mole of our dibasic acid produces 2 moles of H plus and 1 mole of sulfate ions. If we get phosphoric acid, 1 mole of the H3PO4 gives 3 moles of the H plus. Again, we're assuming full dissociation. All the equilibrium is over to the right. Okay, and these are generally, and we'll tell you whether they're strong acids, so it should be in the exam, they'll say whether these are strong acids or not, but I would recommend that you remember at least HNO3, H2SO4 and HCl, and it wouldn't be bad to remember phosphoric acid either. Now let's do a quick calculation. So if I take that up here, and I can use that, so what we have, and what we can have, is let's start off here with a 0.5 mole per decimeter cubed solution. So we've got 0.5 moles per decimeter cubed. Now that means we can assume that 0.5 moles per decimeter cubed is going to fully dissociate, and that means that our hydrogen ion concentration is going to be 0.5 moles per decimeter cubed. So we don't need that anymore. So basically that has literally gone. It has dissociated, and all we've got here is 0.5 of this, and we've also got 0.5 of our nitrate because it's a 1-to-1 ratio. But I don't care about the nitrate at the moment because I'm going to do a calculation. I'm going to do a calculation of pH. So we have our calculation of pH, which is pH is minus log of H plus. We now know our H plus because we assumed full dissociation, 1-to-1 ratio, so therefore that's fully dissociated. We've got 0.5 moles of the H plus. So all we do is put it into the pH equation. We do minus log, and please just do this, don't wait for me to do it. pH equals minus log, and then we go 0.5, okay, and that's moles dm cubed, okay, and there we have it. And all we do is put it into the calculator, use a different coloured pen, and that will equal 0.3. Now, question you've got to ask yourself, is that correct? Okay, not correct, because the tip at the start was it would have 2 decimal places. So it's 0.30, no units whatsoever, pH doesn't have any, okay? And that is how you just take a strong acid like this, use the ratio from the fact you know it's fully dissociated. So in this case it's a monobasic, so 1 will produce 1 mole of your H plus ions because it's fully dissociated. Put the 0.5 into this equation, and therefore you get your pH. So we're going to do sulfuric acid, and we're going to do phosphoric acid as well. So as you can see here, we've got 1 mole going into 2 moles of this H plus. I want to make it absolutely clear, look, there's no moles of this left. It's fully dissociated all the way over to the right. Okay, now if that is the case, we can just quickly put it into the equation again and just say pH. pH is going to be negative log. Okay, so we look here, 1 mole gives 2 moles per decimeter, so the ratio is 1 to 2. So you see 1 to 2. So I know, in this one, I'm going to say that I have a 0.5 mole per dm cubed solution again. So I've got 0.5 dm cubed of H2SO4. Now we've got 0.2 to 0.5. So if you think about that in terms of the log, here I've got to put the H plus concentration here. So if it's 1 to 2, so if this is 0.5, this will be 1. Okay, so that's what you've got to do to the overall concentration. If I have a concentration like this, and it is dibasic, you've got to times it by 2 because you're going to get 2 moles of your H+. If that is the case, we can then just go over here and put our numbers in, and you can see that that is 0, but again, is it 0? No, it's not. It's 0.00 if that is the case. Okay, so really important, 2 decimal places. So our final example of calculating the pH of strong acids is to go for phosphoric acid. So you can see ratio here is 1 to 3. Now again, just emphasising it's fully dissociated, so therefore none of this left. We've just all got this. And again, just pH equals minus log. Okay, let's just fill that in. And then we're going to put our H plus concentration. Now we're going to go with the 0.5 moles per decimeter cubed again. So here we have 0.5 moles dm cubed of our starting material. That's the first. Remember, it's a 1 to 3 ratio. So 1 times 3 is going to be 1.5. Okay, and that's 1.5 moles dm cubed. Okay, put that into there, and then we can go that like that. Put it into our calculator, and we suddenly have a minus number. Okay, and we're starting to get into the minuses to show you can go below 0. And again, this is just how we use a monobasic, a dibasic, and a tribasic strong acid, and we can calculate the pH of it really easy using pH equals minus log of H plus concentration.